Science tells us the Earth rotates at 15 degrees per hour. 15 degrees per hour times 24 hours equals 360 degrees. One full rotation equals one Earth day. Likewise, the heliocentric model claims Earth's rotation makes the moon drift westward across our sky at 15 degrees per hour. So let's take a look at some real-world data to see if science's claims hold up to our observations. This is a very simple test you can do yourself. Go to sumcalc.org, select a time, and note the azimuth. Now move the time forward 1 hour and find the difference between the new azimuth and the old one. Repeat this for all the daylight hours, and you'll see the sun's movement across our skies varies dramatically from hour to hour, rather than maintaining a constant speed at 15 degrees per hour as stated in the heliocentric model. The globe model's varying orbital speeds and planetary tilt only affect the sun's apparent movement across our sky by 0.005 degrees, so this doesn't account for the changes we see hour to hour. It's also important to note that the globe model claims that the sun's apparent motion across the sky matches the Earth's rotation with 99.7% accuracy, meaning that any large deviations from the 15 degree per hour rotation falsifies the model. To expand on our observation, let's plot 3 locations on the same latitude and measure at the same moment in time. We start with Philadelphia on the 40 latitude north at noon. The observer sees the sun at an azimuth, or compass direction, of 140.2 degrees. Moving the time forward 1 hour, the sun is now at 175.2 degrees relative to the observer. This is a change of 35 degrees at 1 hour. Next, we take the same measurements in Denver, Colorado, also on the 40 latitude north. As Denver is 2 hours behind Philadelphia, we select 10 a.m. as our starting time to ensure the measurements are taken at the same moment. The sun's direction at 10 a.m. is 103.3 degrees. We move the time forward 1 hour, and the new azimuth is 118 degrees, 14.5 degrees in an hour. Our final measurement on the coast of California yields a sun speed of 10.4 degrees per hour. So at the same moment, the sun is moving 35 degrees per hour in Philadelphia, 14.5 degrees per hour in Denver, and 10.5 degrees per hour on the coast of California. Let's try one more example to be sure. At noon in the Bahamas, the observer sees the sun at 104.3 degrees, and an hour later at 146.7 degrees. The sun has moved 42 degrees across the sky in 1 hour. Now let's contrast that to a location in Egypt on the same latitude at the same moment in time. At 7 p.m. local time, the sun is at an azimuth of 286.5 degrees, and an hour later it has moved only 6 degrees to an azimuth of 292.6. So what about the moon? Remember that science claims the moon moves at 15 degrees per hour across the sky due to the Earth's rotation. To test this claim, we'll plot locations on the prime meridian, 90 degrees east, 180 degrees, and 90 degrees west longitudes, and measure how fast the moon moves through the sky at the same latitude and time. As you can see from the results, the moon moves at a different rate through the sky at each location. How is this possible in the heliocentric model with a single sun and moon and an Earth required to spin at 15 degrees per hour to give us our 24-hour days? Or on the popular flat Earth model with a single local sun and moon circling at 15 degrees per hour? It's impossible on either model. The only way to explain the behavior of the sun and moon is that we all see our own local celestial bodies which act independently of other locations on Earth.